All right, so let's look at concurrency with Go, and here are the files we're going to look at. And again, if this is the only video you're watching, you can see this code on GitHub at goes to 11 Golang training, right there. Boop 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 boop. Golang training. And here's the first example without concurrency. So we basically have func main. It's going to call and run two functions, foo and bar. Foo and bar are each going to run from 0 to 44, so 45 iterations. And the first one, foo, is going to print foo, and then the number of the iteration. The second one, bar, is going to print bar and the number of the iteration. And this is when we talk about how do programs, read the code or run the code. We're talking about program flow. And there's different control flow. And so sequence control flow is basically it reads it from top to bottom. Basic control flow is sequence, iteration or loop, and conditional, so switches and ifs. Right? So sequence, iteration, loop, basics. And as we go top to bottom, right, the first thing it does is it does some sort of initialization process and figures out everything that's on the page. And that's why I could have these foo and bar declared before main. Main's the entry point to the program. And then it runs foo. When foo's done, it runs bar. So it just runs in sequence. This is running on one thread. Okay, so this is one routine, one thread. And the one routine is the main routine, and that's it. So it's going to do exactly what you think it'd do. Whatever, I can't speak. It's going to do exactly what you'd think. There you go. And let's just watch it. Change directories, going to 22 and 01. Go around main. And so there's all the foo bar from 0 to 44 on each one. All right, so that's no concurrency. There's no concurrency in there. If we want to add concurrency, that is it. Look at the difference between these two programs. What do you see changing?
No. Command go.
That's it. So that's how you do concurrency. We are launching different routines, different threads. They're Go routines. And so, and here we're getting to the edge of my understanding, but Go routines are different than threads. So you could have many Go routines running on one thread. You could also have many Go routines running on many threads, right? Threads have a higher cost just on the system architecture level in terms of how much memory do they use, things like that. Again, we're on the edge of my understanding, so this might not all be accurate. But Go routines, right, have a really low cost. So you can launch a lot of Go routines, and it's not expensive, and it will put them on the same thread, or it could put them on different threads, different CPUs. And so for understanding, this is concurrency. Let's watch it work. So change directories, 02, and go run main. And what happened? Let's see it again. Well, it's not printing anything out, so that's brilliant. So why is that? The reason that is because, okay, we got one. Here's the second question. How many routines, how many Go routines are running on this page? The minimum number. We'll just say the minimum number. What's the minimum number of Go routines running on this page? 3. We have 1, 2, and then we have func main, 3. So we have the main routine of the program. And then inside the program, we launch 2 more. So we have a minimum of 3. I'm just going to say 3. But I'm saying a minimum of 3 because just maybe there's like other stuff happening I don't know about. I'm pretty sure it's just 3. That's it. Right? So we have 3 routines. So this one is running. It launches foo. It launches bar. And then it exits. It's like, go foo, go bar, done. Right? And so those guys are like, okay, I'm going to. And then right before they get to go, they're like, I'm going to go. And then the entire program just shuts. Because when main exits, the program's over. You're done. Right? And so we got to fix that. And to fix that, we could use something called a wait group. So when you look at doing concurrency, right, there's a couple of things you could do to help you manage concurrency. And concurrency is having many different things happening at once. Right? Like, let me multitask. Let me drive and talk on the phone and, I could dial phone calls or I could drink my coffee. Right? Concurrency is like doing all this stuff at once. And that's different than parallelism, which we're going to look at in just one second. So they're related. But when you do concurrency or parallelism, some of the things you could use are like wait groups. to help you synchronize your code. You could use mutexes, mutual exclusions, right? You could also use atomicity. And so these are different ways that we can make sure that we don't get race conditions. And you'll see what all that stuff means in just a second, right? How many people, I just kind of got some confused looks. So, okay, wrap our heads around it. So you're going to get exposed to a few new concepts. And so here I just create a wait group, and it's from the sync package. So if we go and we go to godoc.org, and we go to sync, right? There's sync, package sync, and we're looking for a wait group, right? And so here's a wait group, and you can see we also have a mutex, right? There's a read-write mutex, and then here's a regular mutex. Okay, and so these are things which could help us sync, I guess. I've never worked with any of these other ones. But let's look at what a wait group is. A wait group waits for a collection of Goroutines to finish. The main Goroutine calls add to set the number of Goroutines to wait for. Then each of the Goroutines runs and calls done when finished. At the same time, wait can be used to block until all Goroutines have finished, right? So block meaning don't let the program exit until all are done. So when we have a wait group, we also have these different methods available for it. When we have a pointer to a wait group, we have add, and we have done, and we have wait. So let's look at that. So here I say give me a wait group, right? And then to the wait and sync wait group, sync wait group. Sync wait group is just a wait group. And I'm just wondering why I need, oh wow, that's interesting. Okay. So I get my wait group, and I'll talk about that in 1 second. We get my wait group, and then I add 2 to my wait group. And then I launch these 2, and then I say, hey, wait. And that's going to wait until that goes to 0. Wait group goes to 0. And right here, wait group done means, okay, now I go from 2 to 1. And then wait right here, wait group done means the wait group goes from 1 to 0. Okay, now I'm done. It's at 0. And so when I run this, it prints everything out. And it ran bar first, interestingly, even though it was called second. And then it ran foo. Right? So we could see that this is no longer going in sequence, because we called foo first, and foo ran second. I have no idea why that is. And now foo ran second again. I got you all excited for nothing. Foo's always running second. I have no idea why.
Didn't
Right?
mix them up, though.
Huh?
Didn't mix up our...
It didn't mix them up. Right? And so I guess it just figures out how much code do I have to run, and it just allocates so much time to each process, each routine. You're going to see things running in unison a little bit more. A little bit of a tangent here. You saw me freak out a little bit and go, oh, that's really interesting, right? And the reason I did is because I'm creating a variable WG of type wait group from the sync package. I'm creating a variable WG of type wait group from the sync package. And then I was over here and I was like, well, if I have a pointer to a wait group, then I have these methods. I don't have a pointer to a wait group. I just have a wait group, and those are 2 different types. How's that working then if I didn't get a pointer to a wait group? Well, there's this thing called method sets, and if you look at the documentation, Golang spec, if you look at the documentation, under types, we have method sets, okay? So there are method sets. And if you go read what method sets are, right? Blah, 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 blah. Okay? And basically what that says, and it's a little bit hard to interpret until you see somebody until somebody shows you, oh, that's what that means, is when we talk about interfaces, we have here method sets. And if you have method sets, you could have, and let me put this all together, bring this in. Let me do this one, bring this over. I want this one. There we go. All right. You could have, right, here is my receiver, and I could have a value here, or I could have a pointer for the receiver. So right here I have a pointer receiver, okay? And when I have a pointer receiver, what the heck? Okay, I think I might be confused, but value receiver, a value receiver can take a value type, a value receiver can take a pointer type, a pointer receiver can take a pointer type, but a pointer receiver I don't think can take a value type. So I thought I was going to have a solution there, but I might just be digging myself into a hole where it illustrates that I don't have full command of the language yet. So when I run this, I'm at pointer receiver value type go run main. And it's like that, right? So when I have a pointer receiver, I can't use a value type. So that code right there, I have a pointer receiver, and I'm trying to use a value, right? Circle, and circle right there is a value, right? That circle's a value. And so this doesn't attach the method because I have a value right here. This is of type circle, right? That is what that is. And here, this needs to be a pointer. And so that doesn't run. It says circle does not implement shape. Area method has pointer receiver. Circle does not implement shape. Area method has pointer receiver. So circle, right here, does not implement shape. Area method has pointer receiver. And to implement shape, you need to have an area right here, area function. I don't have that, right? Because this isn't attaching to there. But if I was to do this, like that, and now circle is a pointer, so a pointer receiver can take a pointer type. So C is now of type a pointer to a circle. So now if I run that, it worked. Whoa. Do you see that? Like, you know, a pointer receiver can only take a pointer for things to work, but a value receiver can take a value or a pointer. And the reason that is because there's a parallel type system in Go, which is used with constants. And the reason that they had to create a parallel type system with constants is because, like, the number 42 is a constant. If I just use the literal value 42 or the literal value 7 or 39, that's a constant. What is its type? It's not defined yet. When you could have undefined and defined types. Sorry, this is like all the stuff that over the last 10 days I've been like pouring myself into Go, creating this R training. But you could have defined and undefined types in constants. And so I could define that, hey, constant age int equals 42. And now that is a typed constant. I could also have untyped constants. And the reason there are untyped constants is because if you're just going to use a literal value in your code, you need to be able to have just an untyped constant in a strictly typed language. Otherwise, I'd have to say conversion int and then 42, right? Convert that int and say it is a 42 as opposed to just using 42. And since there are untyped constants, that means we might not have the memory address yet for it. We might not have the memory address. It could be existing on the heap, the stack, or it could just be like something that it never made it to the heap and stack. And this is like what I learned in some of my trainings. It could just be running, you know, at the CPU level and stored in one of the registers, you know, and it never had a memory address. And so if you try to use a constant, right, a value, and give it to something that needs a memory address, it can't just implicitly say what's the memory address because there might not be a memory address. And so that's why with a pointer receiver, you can't use a value. So that's all just to illustrate what I was tripping out on, and it didn't give me an answer because here, if I've got a pointer receiver, maybe I won't be able to attach a value to it, but for whatever reason, I was able to. So maybe there's something in the code further down which would show us, you know, how to see. They just do a wait group, and then wait group add, and they're using all the methods. So maybe something in the code there allows it to be done, but all right. So that was with the wait groups, and we saw it printed all of the bar stuff and all the foo stuff. And then the next one is I'm adding some sleeping into each one. So each time foo prints 1, it's going to sleep for 3 milliseconds. And each time bar prints 1, it's going to sleep for 20 milliseconds. And so we have different sleeping there. And so since we were saying, hey, sleep on this one, well, there's time that the CPU is not being used. So the CPU could switch to the other task, right? So we're running these things concurrently. I don't have to wait until this one is finished right here to then move on to the next one. So while this one's just waiting, I'll do some of the other stuff. All right, so let's see that. See you, Rio. This one is, which one am I in? 4? Yeah, there we go. Oh, I'm in the wrong. So there you could see how it ran. Let me clear this out and run it again. So it was doing foo. It started with foo this time. And who knows how it makes those determinations. But it started with foo, and then foo was sleeping some. So it said, all right, let's start doing some of the bar. Right? So, oh, it started with bar, and then bar slept. Sorry, it started with bar, and then bar slept for 20 milliseconds. In that 20 milliseconds, it did 6 of those. Why would it do 6 of those in 20 milliseconds? Why not 7?
6 times 3 is 18.
Yeah, right? So like, hey, I got 20 milliseconds. Let me do 6 of those. Those each take 3 milliseconds. Maybe, you know, and it has its own way of figuring out what to do when. But then it did bar, right? And then bar sleeps for another 20 milliseconds. So it does 1, 2, 3, 4, 5, 6, and then bar 2, and then 1, 2, 3. Anyhow, so you can see how that's kind of those processes are running concurrently. Okay. And so here is concurrency versus parallelism. This is a great image. Right, so here's concurrency, this bottom one, and I have 2 things that I'm launching to happen, but my CPU can only do one thing at a time, and so those are both running at the same time, but it has to do like, first I'll do some of this one right here, and then I'll do some of this one, and then I'll do some of this one, and I'll do some of that one, I'm doing some of this one, I'll do some of that one, this one, that one, this one, that one, right, that's concurrency. So it can only do one thing at a time, but it's got 2 things going, so it just switches between them. It's drinking your coffee and talking. I could drink my coffee or I could talk. I could do both those things at the same time. I have both tasks running. I'm holding my coffee mug, but I have to stop talking to take a drink, right? And when I'm taking a drink, I can't talk. And to talk, I got to stop taking a drink and I can talk. So parallelism is I'm able to drink and talk at the same time, right? I'm doing those 2 tasks concurrently and in parallel. So maybe a better one would be, I don't know what the example would be, driving and talking. I could drive and talk at the same time, right? So here's a parallelism. And before Go 1.5, you only ran on one CPU. That was the default. After Go 1.5, the default is to run on more than one CPU. Whether it's the max CPUs or not, I don't know. But you can look that up if you're curious. But it runs on more than one CPU now. And so if you wanted to just make sure that you're running on all of your CPUs, here's the code you put in. So now I have whatever many cores in this computer. Start.
If there's only one core.
i7, I think that's a quad core.
Yeah. If you only have one core, can it only run one thread at a time?
Generally speaking, and this gets complex and also goes past, goes into the areas which I don't understand. Generally speaking, one CPU, one thread. And that's what I got from my training when I was looking at this stuff. And if you look into that, you'll start seeing things, how many threads per core, right? Itanium 9 launched with 8 threads per processor. Now, is a thread different than a process? Right? Like, can it only do one thing at a time? Really is, thread versus process. Threads are used for small tasks, whereas processes are used for more heavyweight tasks. Basically, the execution of applications. Another difference between a thread and a process is that threads within the same process share the same address space, whereas different processes do not. So let's look at processes per CPU. So anyhow, that's what you'd start looking into, but who cares? I kind of do care, but there's only so much you can know.
Yeah.
If you find the answer, let me know. I'd be interested. So so here I'm saying, hey, run on all CPUs, and then I'm just running all that stuff again, and maybe is probably the same result, right? Because because by default after 1.5 you're already running on so many CPUs, and currently I'm using 1.5.1. So now when I run it, I wonder if it's the same. Bar and then 6 foos, and then bar and then 6 foos. 1, 2, 3, 4, 5 foos that time. So it figures its own way out to do that. All right, so that's that's parallelism and concurrency. And then here's a race condition. So a race condition looks like this. And we can look at Golang, GitHub, Arden, Studios, Go Training. And then when we're here, we could just search this repository for race. And then here's like a race README, data race. And then here, look at that. So here's a great illustration of a data race. So here is kind of like we've launched two functions, and then we have a counter, which is a global variable. And so function 1 reads the counter, gets 0, and then it yields the thread, right? Counter 2 reads and gets 0. Counter 1 adds 1 to the counter and then writes that back, right? And then this one writes 1 to its 0 and writes that back. So you can see, whoops, that should actually be 2, because we had 2 processes which are trying to increment something. But because they were interleaved, their processes were interleaved about when they read and wrote, there was overlap, we had a problem. So we need to lock this down. We could say, hey, when you're going to write to counter, only you can write to it. So when you read it and then write, only you can do that. And everybody else has to wait. And when you're done, then other people can. All right. So here is a race condition. So I changed the name to incrementer just to give it some abstraction. I'm passing in foo and bar as a string. And then I'm just printing out right here, that string comes in. And I'm printing out right here, hey, is it foo or is it bar? Which function call am I running? Because I call incrementer twice on 15 and 16. And then I do my wait group, and I wait right here. And then when we're all done, we're going to print the final count. And then when I call these 2 functions, I'm going to loop from 0 to 20. And I'm going to get the counter variable and assign it to x. And then I'm going to increment x. And then I'm going to sleep for a certain duration. And then I'm going to take that x, and I'm going to write it back to the counter variable. And this duration will be random, somewhere around, I don't know, 3 milliseconds, right? Random, 0, 1, 2, 0, 1, 2, 3 milliseconds. It'll be random how long it sleeps. And so since these 2 processes are running in unison, right, there'll be times where one, gets this variable, adds 1 to it, and then the other one, so there'll be times where we get a race condition, right, where they're overlapping each other. And so they're getting miswrites. And so we'll see that. And so that's basically it, right? And let's just watch it run. So final counter, 20, 19, 19, 20, 18. All right, so there is some like the random factor in there, right? And so we have the counter going from 1 to 2, back to 1, to 2, to 3, to 3, right? 4, 5, 6, back to 4, 5, 6, 7, right? 8, 7, 8, 9, 9, 10, 10, 11, 12, 11, 12, 13, 13, 14, 15. This should have been 40. If we have 2 things going to 20 on each, and they're going to be writing to 20, right? Each one writes to 20. So 2 things add something 20 times, add 1 to something 20 times. That should be 40. Does that make sense?
Yeah. Can you go back to the diagram?
Yeah.
I'm confused about why it doesn't yield the thread between the right counter 1 on the left and the right counter 1 on the right. I mean, when it flips back to the other one and the other one counts, adds to the counter, that's not yielding the thread over?
I think, yeah, so yield thread means, okay, now this one could go. So this one went and then said, okay, now the other one can go, so you go. And then this one yields, so it goes back over here. And it's like, okay, I'll add one to counter and then I'll write it, right? And then like there's, I guess, a pause right here. So why that one pauses is this one finishes up and writes it, right?
Oh, so the two threads are going simultaneously?
Yeah, both these two functions are going simultaneously. And there's thread 0 and thread 1, right? Which is kind of, I don't know if that's the best way to describe it. So don't look into it like, don't try to get like too precise with this diagram. The main thing is if I asked you, the main thing is this, right? Like you each read the variable and you each get 0, and then you each add 1 to it, and so it becomes 1 and 1. And then you each write that back, and the value of the counter is only 1 when it should be 2. So we needed to like have some sort of access control, to prevent read-write problems, right? So that's sort of what that does. So we can prevent that with a mutex. And so here I've added in the mutex, and mutex stands for mutual exclusion. And so I'm locking right here. From there to there, I'm locking. So when I lock, nobody can do anything except for this one person, right? This one function. And so this one function then increments counter, right? And prints counter and then unlocks. And I could have, instead of having this code here, I could have had, instead of plus plus, I could have had this, right? Same code from over there. And so I didn't necessarily need that, right? I could have done it, let me just take that out. I could have done it this way, where I get the value from counter and then add 1 to that, and I take that value and I write it back to counter and I wait some duration of time. But that's all locked. That's all in here that only one person is doing it, so why make anybody wait? So let's get rid of that. And instead of assigning to a variable and then incrementing the variable and then taking that value and assigning it back, And the reason we had this set up this way before, over in this file, the reason we had it set up that way before is so that right here we could put in a delay. And so we got different values. This, one function reads it and goes from 0, and so I got 0, and then I make it 1, and then I'm sleeping. Another function reads it and it's 0 because this hasn't been changed yet, and they get 0, and then they do 1, and they're sleeping, and then I take my 1 and write it back, and the other function takes their 1 and writes it back. Well, it should be 2, but it's only 1. And so I built that race condition there with a pause, just to sort of illustrate a race condition. If I just done counter plus plus right here, the chances are that that happens so fast that I might not have had a problem. We could have tried that, right? Do you see what I did there and why? Yeah. But here, I don't need all of that sort of like give it to something else and pause. All I need is like basically add 1 to counter. Because it's locked, right? So it doesn't matter. When I have access to this variable, nothing's going to happen. Nobody else can touch it. So when I run this now, whoops, what did I just do? Where are my change directories?
I don't see why that prevents it from having the same problem.
The lock?
Yeah.
So lock, mutual exclusion, means only the function that is then at that moment trying to access counter. It says nobody else can access it. Hold on, I'm doing it. I did it. Okay, now anybody else can access it.
But they're still going to start interleaving.
Yeah.
They're still going to come off the same alternating, aren't they?
No, because they are running. And so basically what this does is right here it says, okay, what's the value of counter? It's 7 or whatever.
Oh, and it adds
Make it 8. Okay, and the value of counter up here is now 8. I'm done. Somebody else grabs it. Oh, it's at 8. Okay, I'll make it 9. I'm done, right? So now this is 9. Somebody else grabs it. So here we go. And so we could see the mutex working. Bar is the first time through. Makes the counter 1 because it starts out as 0, the 0 value. Foo this is the step in the process, right? This isn't the value. This is foo's when I is 0 for foo. So that's the incrementer in the loop, in the incrementer, the incrementer in the incrementer, the incrementer in the iterator. It's the incrementer in the loop. So foo's first time through, it makes counter 2. Bar then goes for its second loop, which is I1. It makes counter 3. Bar then goes for its number 2, where makes counter 4, makes counter 5, and then foo jumps in for some. But you can see counters just going up. So no matter who accesses it, they're the only ones who have access, and we get a perfect 40, right, from 1 to 40. How many people find this interesting? Because we've gone over 20 minutes. We're at 40 minutes. Yeah, I think it's really good. And this is a really clear sort of pathway to understand concurrency, parallelism, Goroutines, and then some of the tools we use to prevent race conditions, like mutexes. So that's a mutex. And we could also prevent a race condition with atomicity. So there's a package, sync atomic. And sync atomic is, if you go look at that, we'll go look at it. Godoc.org, sync atomic. Provides low-level atomic memory primitives useful for implementing synchronization. Require blah blah blah, warns you. So adds int64, automatically adds delta to address and returns the new value. That sounds like totally military. So adds delta, how much do you want to change this value by? What's the change? Delta in math is change. I'm going to change it by 1, right? And what's the address of the value I want to change? This is it. And then it gives me back the new int64. It changes the value and gives me back the new value. Why do I need to pass in the address? A pointer to int64? Why does that function want the address? Same thing. I was thinking it might show me something else. Because I'm going to change the value, right, at that location. And here, maybe we can see it right here. Let me open it up. Atomicity. And right here, add int64 wants a pointer. And add int64 takes an address. Address int64 returns a new 64. All right. I was thinking it might show me some code where it's like changing what's at that address. So when we run this counter add 1, right? It will add 1 to counter, and only one person can change that value at a time. That's the way atomic works.
So if you had made a variable instead of a pointer and changed the variable, it might have made a new address for the new variable instead of using the same address and keeping the variable.
Oh, right here. I think it just throw an error, but let's try that.
But is that the reason? So you don't start multiplying the variable in different addresses? But always keeping the same. You're only dealing with one.
Well, you do the address when you want to mutate something. Cannot use counter as type. Cannot use type 64 as type pointer to int64. Right? It's wants a pointer to int64. So there I give it a pointer, and then I run it, and it goes all the way to 40, and it's taking turns, right? Or whoever has it. And you can see here, wait, 1, 3, 2, 4, 5, 6, 7. That's really cool. Because they both grabbed it, right? And one changed the value and the other changed the value, but this one printed faster. This one is faster at sending it to standard out. So it did it all correctly, but this one just printed before this one because they're running at the same time. Does that make sense?
So you end up with a bunch of bars at the end because food's running faster.
Yeah, there are a few more bars at the end.
I thought food would have finished first completely.
Who knows why it chooses which one it does when. And we got, so here is with a race condition.
Oh, they're both running at 3 milliseconds. Okay. You
Yeah.
took away the difference.
Here's with the race condition. I need to get rid of that package now.
It uses voodoo magic to figure out which thread to run first.
Voodoo magic.
Voodoo magic.
Well, that's working fine. I think it's always going to be 40 after this many tries. Anyhow, if we had some other, if we did this again, right? Now it will erase us. Now it's racing. Make sure we're on. There we go. So it's atomicity. And then finally we have channels. And so channels are pipelines, kind of, into which allow us to communicate between different processes running, different routines. And so there's a saying in Go, right up here at the top of the atomic package. Share memory by communicating, don't communicate by sharing memory. And so sharing memory by communicating is like, hey, I'm passing a value through a channel. And communicating by sharing memory is like, here's the memory address, change it. Right, whenever you want, and let's lock it down. So the way you can think about channels is like track and field. Okay, and so there's a really, like, people who are in a relay race. And so there's a really nice example. So if we just search the Golang Arden Labs Go Training repository for baton, we get this really great example right here. And so let's just copy that example. And I'll just make that 10. Arden Labs baton example. Runner 1 running with baton, runner 2 to the line, runner 1 exchanging with runner 2 running with the baton, runner 3 to the line, runner 2 exchanging with runner 3, runner 3 running with the baton, right? Runner 4 to the line, runner 3 exchanging with runner 4. So just like in a relay race, one runner runs with the baton at a time, and all other people are waiting, all other runners are waiting to receive the baton before they can run. Okay? So it's the same way with a channel. So if you're going to send a message over a channel, if there's somebody waiting for it, they're waiting for the baton. They're waiting for that message, and they don't get a go until they receive that message. So it allows us to sync channels. And so if we look at the code on that, and we'll come back to the baton code here in a second. But right up at the top, I got my counter variable, and I'm going to make 2 channels that I could communicate on. One channel I'm just calling C, The other channel I'm calling done. We're using make because a channel is a reference type, and it has an underlying data structure, so you have to do some setup, or Go does. And so what are the other reference types we use make with?
Slices or
Slice. A slice is built on top of an array. And then what's the other one?
maps?
Map. Maps are built on top of hash tables. Hash tables are built out of arrays. Right? So slices, maps, and channels are reference types. Awesome, Kai. Awesome, dude. I don't know how you pulled that out of your hat because you missed a couple of classes, but that was sweet. All right, so you've been reading or something on your own. So I make two channels, and then I just have a variable x, which is an int64. When I have an int64 or some sort of 64, right, I start thinking atomic, because normally we just use an int. So if you see int64, oh, is there some atomicity going on? And so then I launch my two functions, foo and bar, and I launch another function I called polar. We'll see what that is. And then here, when you put something onto a channel, here I'm putting something onto a channel, so the arrows point towards the channel, right? And then here, I'm taking something off of the channel, so the arrow's coming off of the channel. So I think of channels kind of like garden hoses or pipes between two locations. You know, something goes into the hose, it's going into the channel. Something comes out of the hose, right? It's coming out of the channel. And so the incrementer, we give it a random sleep between 0 and 3 milliseconds, and we put 1 onto the channel, and then we print which other one's running, foo or bar, and we print the number of the iteration through the loop, and then we say if I is equal to 19, right, meaning I've gone through all of this is my last loop, right, 20, I'm going to get kicked out. So if I is equal to 19, I'm adding 1 to my variable x, and I'm locking that down when I do it because I'm not using channels for that, right? And the reason I'm adding 1 to x, and this will just print out the value of x, and I just put those there so it'd be easy to find in the command line. The reason I'm adding 1 to x is because when x is 2, right? Meaning both of those functions have run, I'm going to close my channel. If there are still values on the channel, they could still be pulled off. And so here I'm pulling the values off of the channel. And all three of these are running at the same time, right? So here I'm pulling values off of the channel, and I'm assigning it the value to I. But I'm also checking to see if there's more values on the channel. And if there are more values on the channel, I'm going to add whatever the value I just took off the channel is to the counter. And then I'm going to print the value of the counter. And if there aren't more, meaning my channel's closed and I've pulled everything off of them, I'm going to add true. I'm putting something onto the done channel. I'm putting the value true onto the done channel. So true is getting put onto the done channel. And then I'm going to close done. I'm going to return. This program started running, right? It launched those 3 routines. And then right here, it became a baton runner waiting for the baton. Oh, you want me to receive something? You want me to receive something from the channel done? Okay, I'm going to stop and wait for it. So look at this, right? That's what main did right there. Main put his hand back, and he stopped on the track and said, I'm waiting to receive that baton off the channel, and I'm going nowhere till I get it, right? So that's where putting something onto the channel, if you're a runner and you come running up where you're supposed to pass the baton and nobody's there, well, okay, I'm stopped. This is where I pass the baton. Nobody's there, and I'm stopped. I'm waiting here. I'm holding out the baton. And then as soon as somebody takes the baton, you could start going again. The baton passer could start going again. And the baton receiver, likewise, just stops and waits to receive. And so we have some syncing between separate processes, right? The separate processes would be the runners, right? And those runners have to stop and wait to receive the baton or pass the baton before they can continue. Does that make sense?
Okay. I haven't figured all the code out, but is it possible that the 2 channels or the channel that's doing the counter can finish up before it's been filled up. In other words, if they're still adding to that channel and it's printing or it's counting from that channel, is it possible that it can finish pulling off the channel, but there's still more to come in that haven't come in yet?
Well, I don't close my channel right here
Yeah,
until both of the loops
that's
have finished.
that's what I need to see.
Yeah, so but when a loop is done, it adds 1 to x. And then when x has become 2, right, it closes the channel. So
Okay.
everything's been put on it. Let's close that channel.
Okay.
I'm sure there's a better way to write this code.
No, that's what I was missing.
There's probably some better way to, close the channel when both those are done.
Okay, I see it now.
But I'm not sure what that would be. That was the simplest example I could think of. So when we run it, bar, that comes right here, is 0. First time through the loop, adds 1. Bar puts 1 onto the channel. And then polar receives 1 from the channel. More is true. There's more, right? The channel's still open. And adds 1 to counter and then prints it, counter 1. And then bar is on the iteration 1, right, which is 2. And then it passes 1 to the channel, right? The count and the polar receives 1, adds 1 here, so it becomes 2, prints 2. Whoa. Counter then prints 3. And foo then goes to 0 and puts 1 onto the channel. Foo puts another 1 on the channel, and then now we're at 4. We've had 1, 2, 3, 4, right? But here we've only had 1, 2, and then it printed 3. The reason is because if that looks wrong, that's because you're thinking sequentially. You're thinking in sequence, control flow, one thing after another. This isn't sequence. This is in parallel. So it did this before it did that in terms of the logic, but it printed this before it printed that. Isn't that kind of nuts? So here, right, logically it ran this one and then that one, but then right here's where it puts it onto the channel. Here's where it takes it off to the channel, right? So put it onto the channel, and then it took it off of the channel, and then this one printed right here, got to that line and printed that right here before it got to this line and printed that right there. That's kind of nuts, huh? Whoa, what's up?
Is there a way to control when the thing is going to yield so that you don't run into that weirdness?
Yeah, I'm sure like you could use a mutex, or maybe I could also pass, I think you can only do one value at a time, but I could do a struct, right? And so I could wrap everything into a struct and pass the struct and then print it all at once, right? Pull from the struct and print it all at once right here. Like, who did it come from? It came from bar. What loop is bar in? 1. What's the value counter now? 4 or whatever, right? So that, and then I'd be passing that entire struct. Anyhow, you guys want to see Arden Labs code? Sync group, make a channel. Doing wait groups, we're adding 1. This is in main. And then we send a runner to the track, right? And then we're waiting to receive the value. We're putting onto track the value 1, and we're waiting. Right? So, when all those finish it. And so then down here, we look at this. What is the go runner? First runner to his mark. What is go runner? It runs this function, and it passes in the channel track. So he's doing those as not as global variables. And constant MAC exchanges equal 4. var exchange is an int. And from the track, we're pulling a baton. We're taking the value from the channel track and assigning it to the variable baton. And what did we put on? We put on 1. And so that's like seeding it. And then runner D with baton. So that's 1. Runner 1 running with baton. And baton is less than max exchanges. So max exchanges is 4. So if baton is less than 4, exchange equals baton plus 1. And we say runner 2 to the line. And then recursion kind of, go runner. And we pass in the channel. Right? So go runner, and we call this function again. Right? We're passing in the channel. And when we pass in the channel, it comes back here, and exchange int. And from the track, we pull 2 and add it to baton. Right? And is there a 2 there yet? Yeah, because we put it here. But while that's running, we've also had that first process running. We had a little bit of a sleep running around the track. And then if baton equal max exchanges, runner whatever, finish the race, and we're done. And then we return, we leave that, and we come up here, and that's finished. And then here, runner %d exchange with runner %d. So runner baton and runner exchange. And we take exchange, the value of exchange, and we pass that on to the track. So that's a little bit like, there's some recursion happening there. It's a little bit to wrap your head around. You have to map that out, pencil on a piece of paper, and just like check, see how each of those are flowing. But pretty creative. I'm going to take that example out of here. It's just a little bit too involved. But anyhow, man. That's Goroutines and concurrency and parallelism and weight groups and atomicity and channels.
Can you explain atomicity and the package atomic and why?
Sure.
I'm confused about that one.
So let's say that we are all camping. A bunch of guys went camping up in the mountains. And we have 1 keg and 1 cup. Okay, or we have 1 keg with a hose coming out of it and no cups. That keg's atomic. Only one person's drinking from it at a time. Right? And for somebody else to drink to it, they've got to have the hose. Drink from it, they've got to have the hose.
So what's the purpose of the package?
The atomic package?
Yeah.
So that it restricts access to the variable.
Oh.
So only one routine can access. It's like instead of locking code with a mutex, it's a smaller lock and it's faster, and it's only for reading and writing from this variable.
Okay.
Right? So you don't have to put lock around it. There's less syntax in your code. It's just like this is atomic, meaning only 1 thread. Atomic meaning singular.
Mm-hmm.
If something's atomic, it's singular. Right? Isn't that one of the definitions of atomic?
Mm-hmm. Yeah.
Is it's ever relating to atom or atoms, consisting of uncombined atoms rather than molecules, ever forming a single irreducible unit, right? And so I guess if it's atomic, it's only one thing can access it at a time. All right, so that was like a crazy amount of time. That was a whole hour. I can't believe that took that long. I totally underestimated that. Huh?
I can't believe you got all that information in such a short time.
To you or in my own head?
To me, it seems you went pretty fast.
Oh, okay, yeah. Covered it pretty quick. It took me a while to wrap my head around it. And it's still not, I'm not totally there in terms of like, you saw me like right with that one piece of code. I'm like, there's probably a better way to do this right there. Right? But I was like, whatever. Until I felt like a hack. because I can't just check it off of I, right? Because then, but I should probably look in the weight group thing. Maybe there's something to check, like, or what would I be looking for? I don't know. But it'd be almost super clean code if that big chunk wasn't there. It'd be like, this is just the essence of what I want to show you. But I don't know how to close my channel. Hey, one thing I will show you is like, how do we have one way we could check race condition is we could run this command right here. Go run main.go with the race flag. And so if we have a race condition, so that's 06. And go run main, right? It runs at race condition, should have been 40, did 21. I run it again, I get different values, right? But if I do go run dash race main.go, main.rog, it does it, but then it says, hey, you know what? Found one data race, and if I look up here, it gives me information about that. And it tells me write by Goroutine data race, write by Goroutine 6. So that's why it's like maybe there's more Goroutines happening there because it's 6 and 7. But I was thinking there's only 3 here, right? There's main, there's this one, there's that one. So maybe there's something else happening. And it tells me, you know, here at line 26 and 15, 16. So 26 and 15 and 16, I have a race condition. So these two things are both trying to write to that variable, global variable, and they're overlapping each other. All right, so in the next video, or the next deal, we are going to troubleshoot Google Cloud Storage. I need a 5-minute break. And one thing I will show you is, like, you saw some of my code was not formatted well. Okay, so look at that. My packages are not aligned well. So inside here, I'm going to go up to Goroutines, and I can do go format. If I ran that, it only runs it on a file, whatever file is in the directory. But if I add this, it runs it recursively through the directory I'm in and everything beneath it. So there I'm running go format, and it just ran it on all those files, needed formatting. And now if I look at it, right, oh, that's all nicely got formatted. And then there's also golint. And you have to download golint, but here golint's going to tell me everything I did wrong in my code for not having it be formatted well. So I have a lot of files to fix. But luckily those are on the old folder, so I don't have any files to fix. All right, that's it. 5-minute break.